Hello, John Chamberlain here. Welcome to Fundamentals of Light and Laser, Course 1. Today we're going to do Laboratory 1-5C, Polarization. In Part 1 of this lab, we'll investigate the law of Malus, in which we look at the angle between two polarizing filters. All right, well, let's look at some of the equipment that we're going to be using on today's lab. We have our friendly helium neon laser that we're familiar with. And we have it aligned already with our photodetector downstream here. You'll notice that it's going right into the small aperture of our photodetector. We have one of our polarized filters already mounted into our rotating stage, okay, which we have set up at exactly 0 degrees for right now. We'll have to align that beam so that it goes right through the center of the analyzer. Next, we have our polarizer, which we'll mount upstream and mount it so that its beam goes through the analyzer and then strikes the photodetector. And now what we'd like to do is to rotate the polarizer so that we get maximum power through the whole system, and we'll set that as, interpret that as our 0 degrees for the law of Malus to investigate. Derek, would you like to help me rotate this polarizing filter using the finger cots?
Sure.
All right, we've lined up our helium neon laser with our polarizer and our analyzer, and with set at 0 degrees on the 200 microwatt scale. We're going to take some readings every 10 degrees and let you read those readings yourself. Okay, so I hope you got a nice data table full of measurements every 10 degrees at that power level for the law of Malus as we varied the angle of the analyzer for the laser entering the power meter. Now you probably noticed that our maximum did not occur right at the 0 degree setting for our analyzer. That's a pretty good indication that our laser was probably a little bit polarized coming out. And so we can correct for that by looking for the maximum, the actual maximum. And in our case, it looks like the maximum occurred right about 10 degrees. We've got a reading of about 21.5. So, and the predicted power would be equal to the power out times the cosine squared of the angle, the corrected angle. In our case, that would be 21.5 is our power out of our laser, our maximum power, times the cosine squared of the angles that we recorded minus 10 degrees, which is where we actually saw the maximum. So for example, we'll say at 40 degrees where we measured 17 microwatts, let's see how that predicted value would predict to be at 21.5 times the cosine squared of 40 degrees minus 10 degrees. That would be 21.5 times the cosine squared of 30 degrees. If we put that into our calculator, we get 16.125 microwatts. Okay, and how does that compare with our answer of 17? Well, the percent difference will be about 6% rounded off. That's a pretty good result. And if you can do that for the rest of your values, and you'll see that for the major part of your measurements, you probably got less than 10% error. Of course, when you have very small numbers, a difference of 1 microwatt will be a huge difference. So don't get too alarmed at those small numbers being off by 1 microwatt and having 100% error or something like that. Okay, so that concludes the first part of Lab 1-5C.